We are again with Math with Marty. Seems like only a short time ago that we were last week doing that problem with the golf ball. It was only a short time ago because we actually taped 2 shows in a row wearing the same shirt. I still got the same goofy beard I had last week, and it didn't get any longer in the 15 minutes between taping one show and the other. I'm still considering whether we're going to get rid of it. Well, you see, I went to the barber and, I told him, leave the sideburns, don't cut them right up at the top of the ear. So what, he left me about 1/8 of an inch below the top of the ear. Now, I know it's 1991, I know it's not the 70s anymore, but I'm 35 years old, I just can't get used to this thing. I know we don't go for these 1970s mutton chops. I'm not wearing bell-bottom pants, but leave me halfway down the ear, for God's sake. So until then, I'm not quite sure how I'm going to cut this stuff. We left last week with a problem that got kind of way out of hand with this golf course, that we were taking random shots and the ball kept falling anywhere down the fairway that you didn't know how far it was going to land. And we came up with a big calculation, and then at the end of the show I said, well, here's a problem, and this problem actually arose in connection with a particular way of solving that golf course problem, which I don't know if I even want to get into in this case. Well, I think I will mention the connection. Because it's kind of interesting. If you got 3-dimensional coordinate space, what you got your x-axis, your y-axis, and your z-axis, and you look at a unit cube centered over here, and the unit cube looks like that, and you say, let's consider the region defined by the condition x plus y plus z is less than 1. And that gives you is, this is the equation, as in 3-dimensional geometry. An equation like this always gives you a flat surface. And the nature of the surface is easy to 0, then z equals 1. So it's the plane defined by these 3 points. And if you include the origin, that forms a kind of a prism kind of shape that's sort of a triangular kind of wedge. And the volume of that wedge is 1/3 of the base times the height. Now, the base of this wedge is area 1/2 because it's this triangle, and the height is 1, and the volume of the surface, volume is always 1/3 of the base times the height. So the volume of that wedge is 1/6, which is 1/6 of the volume of the unit cube. 1/6. And just if people remember that golf course question, it's sort of like if you have 3 shots, and your shot could go anywhere between 0 and 1 in length, and it's totally random, and you ask, what's the chance after taking 3 shots that you still wouldn't have got to 100 yards? Yeah, let's say your length is 100 yards. Well, then the condition is that your first shot plus your second shot plus your third shot adds up to less than 100 yards. And out of all the possible combinations of 3 shots, which are represented by points in this 3-dimensional cube, the percentage of shots which fall under this condition is given by the volume of that wedge, which is 1/6 of the cube. So after taking 3 shots, 1/6 of the people still haven't shot the golf ball 100 yards. Funny thing. And that is, in fact, something we can determine on this condition, x plus y plus z less than 1, by looking at the wedge and evaluating the wedge. But the problem I gave last week was to find the volume of the region defined by x is less than y is less than z. It's a little bit different condition. And this condition is actually a little bit harder to write the shape of the wedge. It does constitute a wedge cut out of this cube, but it's kind of a funny shaped wedge, and it's not quite as easy to see as the wedge we did in the other case. But the funny thing is the volume of this wedge is easier to calculate, because of all the points within the unit cube, every point is labeled by 3 coordinates, x, y, and z. Any point in the whole cube is labeled by 3 coordinates. Now those 3 coordinates always got to come in some order. I mean, one's got to be biggest, one's got to be smallest. So what we're looking at here is all those conditions for which x is the smallest of y and z. Now any one could have been smaller. Y could have been smaller, z could have been smaller, or z could have been bigger than y, or vice versa. Of all the permutations of which one is bigger than the other, there's exactly 6 possible permutations. There's 3 that could have been the largest, 2 remaining that could have been the second largest, and 1 that had been left over for the smallest. So there is exactly 6 possible conditions of this general type. For example, we could have said y is less than z is less than x, similar kind of condition. All permutations on x, y, and z. 6 possible permutations which cover every point in the cube, of which 1/6 of those must fall within this condition. So the volume of this wedge is 1/6 of the total volume of the cube. Funny thing. These types of volumes are called in general simplexes, and it's something that can be seen easily in this case, that if you go to 4-dimensional hypercubes and take a volume defined by w less than x less than y less than z in 4 dimensions, that it must occupy 1/24 of the total volume of the hypercube. And we had a solution for that golf ball problem, which I didn't want to do on TV because it got into this hypercubes in n-dimensional space. But this is kind of an interesting aspect of that, which I think I will drop at this point and move on to happier things. Let's clean the board. We've had some rather unfortunate accidents with the board falling over in several shows, and we're going to clean softly so we don't have that occurring again. And there we go. The board is wiped off. How come Johnny Appleseed never gets the board falling on him? I mean, that's what I don't understand. Is it? Yeah, like, I don't know if you're sabotaging my show or what's going on here, but I've never seen the board fall on Johnny Appleseed, or that religious guy with the wide board. The guy who comes on Sundays?
Crazy glue.
Oh, crazy glue. Well, okay. Yeah. Speaking of religious guys, I saw Jimmy Swaggart on TV a couple weeks ago, and he did Amazing Grace. He's a heck of a singer and quite a guy on the keyboards too. They did Amazing Grace, and not long ago we did Amazing Grace on Math with Marty. And so there's Jimmy Swaggart doing it. And of course it's quite different, you know. We did it just as a straight 3-part a cappella arrangement. Jimmy Swaggart had the big organ sound, and the choir was beautiful. And he used some different chords than we used. He went to some of those colorful chords, like he went to an A minor and then a D7th. It was beautiful. And so you see, well, isn't that something? And then the other day I saw it on, I saw Len Fairchuck on the Indian Hour. Now, was he an alumnus of Channel 11, or was he always on the other channels? A long time ago. Well, there's a graduate of Channel 11 that's now on one of the commercial stations, and he was there, and he had a young fellow from the Puckatawagan Reserve on, singing something, and then he had Wayne Link, the guy with the cap, plays slide guitar. Is that called steel guitar or slide guitar when you go like that? And they steel. So he did Amazing Grace. Heck of a player, Wayne Link. Beautiful. And then Len did around on the fiddle. What a guy. And then just the other day, you know, there's that goofy commercial for these kids in a brass band, and they had kind of a Dixieland version of Amazing Grace. So since we did it on Math with Marty, we've spawned a deluge of imitations, you know, from Jimmy Swaggart on down. And we'll just see what happens next time we do a song, and how many people pick up on that. All right, all right. Now, there's a topic I started 2 weeks ago about distortions in solids, and I just got started on that topic when the show ended, and then I gave a problem, and the problem took me the whole of last week's show, and I've already eaten up half of this week's show, and I'm not going to get very far with that distortions in solids topics, it looks like. So let's give it a start and see how far we get. Okay. I said if we had a cube of steel and we pushed down on it so that we squished it down by 1% in this direction. No, I said 3%. I said that it would bulge out 1% towards these directions, towards the sides. And since we expect it to be, behave in a rational three-dimensional manner, we should also expect it to bulge out in this direction, the same degree, 1%. And when I see this, okay, I'm lying. I admit I'm lying because, to me, I don't like to talk about a distortion of magnitude epsilon much less than 1 like they do. I like to put numbers to it, and I like to say 1%, 3%, because you can get a handle on it. And in fact, in actual steel, metallic steel, by the time you stretch it 3%, you've permanently deformed it and altered its mechanical properties. So if I had said 0.003%, I'd be talking literal truth. In fact, it's true up to 3% of 1, or 0.03%, I still would have been basically telling the truth. And then who wants to talk about a lot of decimal places? So I think you can sort of take it with a grain of salt. Then when I speak of distortions like 3% and 1%, I intend them to mean very small distortions, and the critical fact is that the ratios are in the fact of 3 to 1. I think that's fairly understandable. And I apologize to any engineers who have gone out and designed critical structural components based on information from this television show. The studio disclaims all responsibility for personal, liability that could ensue. Here we go again. 3% squishing gives you 1% bulging outwards on each side.